Now here's a rather creepy, scary fellow. See him wander around England with his longbow. The longbows and bows and arrows are really misrepresented in history. They have an incredibly long range, far longer than most people think. Archers would not be generally in a position to be clubbing people and shooting them at 3 feet away. It's a standoff weapon. You want to be way, way back. The peak of these in warfare was about 1350 to 1450, and these bows were made out of yew wood was the preference, and they were a full 6 feet tall. It typically took 150 to 180 pounds to draw these back. The numbers vary, but no matter what, this is in the range at the 150 end. That's already 3 times higher than most modern bows are sold for recreational purposes. So we need to turn these numbers into newtons. 1 kilogram turns to 2.2 pounds, right? We get 68 kilograms, and 68 kilograms is about 680 newtons of force, okay, when we look at our sort of equivalent to it. So we look at about 680 newtons draw strength on these things. That's a lot, okay? That means when your left arm is out, you're holding almost a body weight. It dates to over 2000 BC, and it's a very specialized craft to make one and takes years to train properly on. The draw strength is insanely high. Archers would have been very muscular, and the skeleton showed clear damage and enlargement to the bones, bone spurs, all sorts of stuff. Typically, you drew about 3 feet back, and the technique was to hold your hand here and pull the bow away from you. So if this man is using a proper medieval bow, he's got 68 newtons across his arm here, or 680 newtons, which is 68 kilograms. So that would be the equivalent of him chinning himself, like pushing up on the ground. Pretend the bow is the ground and he's doing a push-up one-handed. It's a pretty good draw. The yew wood itself was nearly harvested to extinction in England, to the point it became a critical war supply. So England even resorted to taxing ships, saying that if you land in the ports at London, in order to offload your cargo, you have to give us anywhere between 1 to 10 pieces of yew wood pre-made for a bow per ton of cargo. So yeah, it was a strategic material at the time. The physics involved turns out to be remarkably Hooke's law. When you draw the bow, the force increases linearly with your pull. Double the pull, you got double the force. And the stored energy in the bow is going to work by this. India had some really cool bows and arrows that actually were rocket powered. So if an archer has a 600 Newton pull at 1 meter, we have 2 ways of calculating the energy in the bow. One, straightforward like this, or we use this formula. But if we use this formula, we have to find K. Since force equals Kx, K is F over X. So the 600 newtons pull at 1 meter means the K value for our bow is 600 newtons per meter. So when I calculate the kinetic energy using it this way, I get there should be 300 joules in kinetic energy, but there's 600 joules when I calculate the energy by a pull. They don't match. So what's going on here? 2 different ways of doing it, and they should give us the same number. And those should be the same. So what have we done wrong? I deliberately made a mistake here. You got to look for it and see what your error was. I'll pretend you paused this and you studied this to try to find my error, other than I've got the word calculation instead of calculating. Let's take a look at a common error here. The numbers depart by a factor of 2. That is not a small error. That is a significant understanding error. An error by a factor of 2 means you were on the right track. You've made a simple error that you can find. So never pay attention to how the error was made. we've got these two formulas that are giving us different answers. One of them must be wrong. Here is a plot that an actual archer, hobbyist archer, did at home. So he got into the geek mode part. He displaced, drew the string back, and measured the force with a spring scale. And he got this lovely force distance thing. So the arrow I gave you is really, the only difference is these numbers would have an extra 0 on them for the military longbow. This actual force data shows that force increases linear with the draw distance. This means the force would start at 0 and peak at 600 newtons. Does the fact that the force is not constant but changes as we pull affect one of these equations? Is one of these equations going to be bothered by the fact that the force changes? This one. The trick I pulled off onto you was to give you the maximum draw force. This would be the energy if the bow had the same tension the entire pull. It doesn't. The pull changes from 0 to 600. So it averages 300. So we can take the average of the force. And we'll put in 300 because that's the average force on the bow. And now the answer is correct and they match. Why didn't this changing force affect this equation? Because this equation, 1/2 kx squared, already dealt with the fact that the force changed. I didn't show you the derivation of that formula, but it's already built in. So you got to be careful. You can't use this if the force changes. And so it's a very simple mistake and it's easy to find. You're not stupid. You just overlooked that this formula said constant force and the force is not constant. Okay? Next, we're going to look at calculating the height of an arrow. So we started with 600 joules of energy went into that arrow. Okay? I've goofed. This calculates 300, and then I promptly used 600 over here. So I've got an error by a factor of 2 that's honest, but hey, let's just assume we have 600 joules kicking the arrow straight up. We'll assume a 95.9 gram arrow. I look that weight up. All of this energy now goes to height. So if the initial energy and the final are the same, then the 600 joules in the bow will transfer to this. Solve for height, we get 638 meters. The bow is about 80% efficient according to online data. So if I downgrade the height to 510 meters, and my brain was going, 510 meters, wow. So technically, since I used the wrong value here, this answer should only be about 200 meters. That's not terrible, but it's still a significant way up the side of the CN Tower. And it's air resistance. Air resistance is the part that's doing us in here. And it's not part of this equation. This gives you the launch speed and the potential height it reaches, but in reality, we now then have to take an air resistance into account, and that becomes the second half of a problem, which we don't do in high school.